In this video, we're going to define a local basis at a point. We'll also define first countability and second countability. So recall our previous definition for a basis for a topological space is a subcollection of tau, or in other words, a subcollection of open sets, such that every open set in the topology is a union of members of beta of the basis. Now our new definition, if x tau is a topological space and y is an element of that set, a local basis at y is a subcollection beta sub y of tau, such that y belongs to each member of beta sub y, and each open set containing y contains a member of beta sub y. So in other words, if u is open and y is an element of u, there is some b in beta sub y, such that y is an element of b, which is a subset of u. Let's look at a couple examples. So first, if xd is any metric space, or in other words, x tau is the topology generated by some metric d, and y is an element of the set x, then the balls of positive radius centered at y are going to form a local basis at y. As another example of a local basis, if we look at the set, any set x with the discrete topology, that's where every subset of x is open, and let y be an element of x, then the collection consisting of a single set, the singleton set y, is also a local basis at y. And u open, y is an element of u, then clearly the set containing y is a subset of u, and that is an element of this particular basis b sub y. Great. So here's a new definition for us. A space x tau is first countable, or also we could also say that it satisfies the first axiom of countability if there is a countable local basis at each point of x. So for example, we just saw that for any point y in x with the discrete topology, a basis consisting of a single set is a local basis at y. Countable means countably infinite or finite. So this tells us that x, any set x with the discrete topology, is first countable. Great. Now let's do a non-example. So say that tau sub c is the finite complement topology, then the real numbers with the topology tau sub c is not first countable. Let's see why that's true. So let's show this by contradiction. Let's suppose for contradiction that it is the case that the real numbers with the finite complement topology is first countable. Then let's let y be an element of R, and if it's first countable, that means that there's some countable basis bi, I goes from 1 to infinity, is a countable local basis at y. So we've got this countable local basis at y, this countably infinite or possibly finite collection of open subsets that form a basis at y. So bi being an element of tau sub c, the finite complement topology, means that bi complement is finite for each I. And so let's think about the union from I equals 1 to infinity of bi complements. So we proved way previously in this class that a countably infinite union of finite sets is countable. So this is a countable set. And we could also write that using De Morgan's laws as the intersection from I equals 1 to infinity of the bi complements. So that's by De Morgan. And so this is countable. It's countable. We know that R is uncountable. The real set of real numbers is uncountably infinite. And so this tells us, okay, this tells us that here we've got a countable set that means its complement, the intersection from I equals 1 to infinity of bi, that's all of the rest of R, must also be uncountable as well. So we showed something pretty strong, and all we actually want from that is that because it's uncountable, because it has infinitely many elements, then it has some element other than our original point y. So there exists some x not equal to y, such that x is an element of every basis element, bi, from I equals 1 to infinity. It's an element of every single basis element. Okay, what are open sets in the finite complement topology? The empty set and sets whose complement are finite. So the set of real numbers minus this point, is open in this topology that we're talking about, in the finite complement topology. And because its complement is just the set containing x is clearly finite. And x was not equal to y, so y is an element of the set of all real numbers other than x. But x was in every single one of the basis elements. Because x was in every single one of the basis elements, that means that b sub I is not a subset of this open set R minus x for any b sub I. And that tells us that this collection b sub I is not a local basis at y. As one more class of examples with first countability, every metric space is first countable, has a countable local basis. Let's verify that. So let's let y be an element of x, where x is some metric space, which again implies that it's also a topological space. Then the balls centered at y of radius 1 over n, for n element of the natural numbers, is a countable local basis. So clearly this is a countable set, and we need to verify that it's also a local basis, that y belongs to each member of b sub y. So this is our beta sub y. So is that the case? Yes. For any n and n, then y is an element of the ball centered at y of radius 1 over n by definition. Y has distance less than 1 over n from itself, has distance 0 from itself. And secondly, each open set containing y contains a member of b sub y. So let's let u be an open set, y an element of u. Then in a metric space, we're in a metric space, so that tells us there is some epsilon greater than 0, such that y is an element of the ball centered at y of radius epsilon, which is a subset of u. And we know that there exists some n in the natural numbers such that 1 over n is less than epsilon because it's a positive number. And so that tells us that the ball centered at y of radius 1 over n is contained in the ball centered at y of radius epsilon, which is contained inside of u. And so we are done. We've shown that any metric space is first countable. So here's another definition of second countability. So a space x tau is second countable if it has a countable basis. So not a countable local basis at each point, but just a countable basis overall. And observe that second countable does imply first countable. If we've got a countable basis, then those countable basis elements that contain a point y would be a countable basis at that point y. So second countable implies first countable. As an example, the real numbers with the usual topology is a second countable topological space. It has a countable basis. Let's see why that's true. Well, we know that the rational numbers, a subset of the reals, the rational numbers is a countable set, and that tells us also that the rationals crossed with themselves, the Cartesian product, finite Cartesian product of countable sets is countable. Now, let's think about the open intervals of the form a, b, such that a is less than b and A and B are in the rationals. Now this is not exactly the same kind of set as what we have over here. These are ordered pairs and these are open intervals, but we see the correspondence between ordered pairs of the form A, B, and open intervals of the form A, B. These are sort of going to have cardinality less than or equal to that. So yeah, this is a countable set as well, these open intervals with rational coordinates. And so this is countable. We need to show that it's a basis for R with the usual topology. Let's let X be an element of the real numbers, U an open set containing X. Then, again, by what we know about the real numbers with the usual metric, that's induced by this metric space. So there is some epsilon greater than 0 such that the ball centered at X of radius epsilon, which is equal to X minus epsilon, X plus epsilon, is contained inside the open set U. And now we know that there exist A and B in the rational numbers such that X minus epsilon is less than A, which is less than X, and X is less than B, which is less than X plus epsilon, that between any two real numbers is a rational number. And so therefore, it's the case that X is an element of this basis element, A comma B, which is a subset of U, and therefore, yes, the open intervals with rational coordinates are a basis for the real numbers with the usual topology, and it's a countable basis. So this is a second countable topological space. Recall that a topological space, X tau, is separable if it has a countable dense subset. So a subset A is dense in X tau if A closure is equal to the whole set X. And this is logically equivalent to saying that for any open set U in X, there is some element that is in both that open set and the set A. So we saw that R with the usual topology is separable because the rational numbers are a countable dense subset. And we also, where Q closure is the whole set of reals in that topological space. However, in the real numbers with the discrete topology, that is not separable. The closure of Q in that space is just the set Q, which is not equal to the whole set, because every set is open in the discrete metric, and therefore the singleton elements of U, the singleton sets of rational numbers are each open sets, and so the closure of Q is just itself. So, of course, it depends on both the original set and its topology. So here's a theorem for us. Every second countable space is separable. So let's suppose that X tau is a second countable topological space. That tells us that it has a countable basis, B sub I, and I could range from 1 to infinity, or I could technically be finite. It's the same proof either way, so let's just go with this. Let's then choose one element, X sub I, in Bi for each I, and that means that the set X sub I, such that 1 is less than or equal to I, which is either less than or equal to n or infinity, same proof, is a countable set. And so what we also want to claim is that it's also dense in X. Why is that true? That's true because for each open set U of X tau, it's the case that U is a union of elements of its basis. That's the definition of the basis. So use a union of elements of this collection of countable basis elements BI, and each of those elements of BI contains at least one of these. So U intersected with this countable set xi, 1 less than or equal to I less than or equal to infinity, or less than infinity, is not going to be an empty set. And so that tells us that, yes, this collection of elements xi is a countable dense subset of X. So every second countable space is separable, has a countable dense subset. It's also the case that every separable metric space is second countable. Note here that we have metric space, so this isn't quite the converse of the theorem above, because not all topological spaces are metric spaces. Later on, we will find topological spaces that are separable but not second countable. So for our proof here, suppose that the metric space XD is separable. It's separable, so it then has a countable dense subset, and we'll call that the set A. So then, if we consider the ball centered at A of radius 1 over n for all n in the natural numbers, that is going to be a local basis at A for all A in A. We saw that above, that a metric space is first countable, and we can see that with this countable basis. The ball's centered at that point of radius 1 over n for n in the natural numbers. So how do we get a countable dense subset? Well, what we're going to do is take the union for all A in A of the balls centered at A of radius 1 over n, such that n is in n. Now, this is a countable union of countable sets, and we proved way back when that a countable union of countable sets is countable. In our book, this is theorem 2.3. And so the collection of balls centered at A of radius 1 over n, such that A is an element of this countable dense subset, and n is an element of the natural numbers, is a countable basis for this separable metric space.